You are surfing, wandering in awe. Welcome to Inertia Collect. Come and may what you love. Inertia Collect is my corner of the internet where curiosity meets conversation. It's a journey through books, films, articles, and ideas. Basically, anything that sparks, wonder, or makes us think a little deeper about life. Each episode, I'll share my thoughts, insights, and yes, my fascinations about topics ranging from science and sociology to psychology, philosophy, and beyond. Whether we're unpacking a novel's themes, analyzing a film's cultural impact, or exploring a thought-provoking article, this is a space for all of us to learn, laugh, and reflect together. This episode will be on Gödel's Proof by Ernest, Nagel, and James R. Newman, where we will be exploring how our understanding of mathematical systems was before Gödel's Incompleteness theorem. Well, it is not quite well put if I forget to mention the history of mathematics and unique approaches that mathematicians built throughout our time. We will explore many connections in thinking and logic applications. If you ask my opinion, this episode will give you a starting motive to get into mathematical thinking, revisiting different times where people shared their unique perspectives and contribute to understanding of mathematics and its applications. I enjoyed reading Gödel's Proof. It offers many historical developments in mathematics that I want to know. I think you will find it exciting to discover how solutions can cover many areas in a system and how we come up with solutions for areas of interests.
The historical moment. Gödel versus Principia Mathematica. Today, we're diving into the monumental work of Kurt Gödel, as explored in Gödel's Proof by Douglas R. Hofstadter. To set the stage, let's talk about the historical moment that started it all. In 1931, Kurt Gödel, a 25-year-old mathematician, published a short but groundbreaking paper. The title, which translates from German to something like On Formally Undecidable Propositions of Principia Mathematica and Related Systems, might sound intimidating, and that's because it is. But the impact of this paper was massive. It completely changed how we understand mathematics and logic. Here's the gist of what Gödel did. He proved that within any consistent mathematical system, there are true statements that cannot be proven using the rules of that system. It was like finding out that no matter how smart or complete our tools seem, there will always be questions that they can't answer. This result sent shockwaves through the mathematical world and beyond. Now, at the time, this paper didn't grab everyone's attention. Why? Because it was dense, technical, and required a deep familiarity with a massive book called Principia Mathematica, written by Alfred North Whitehead and Bertrand Russell. Principia Mathematica aimed to establish a solid and rigorous logical foundation for all of mathematics. Another excellent explanation of the author's intentions in Principia Mathematica can be found in Philosophy of Mathematics, a collection of 13 essays from the latter half of the 20th century on the philosophy of mathematics. In this collection, W.D. Hart, an American philosopher and professor emeritus, Nice, provides valuable insights into their work. In the preface to Principia, he said that the chief reason in favor of a theory on the principles of mathematics must always be inductive. By this, he meant that instead of the conventional mathematical wisdom being justified by deduction from the so-called foundations of mathematics, The foundation is justified only if it suffices for the deduction of the conventional mathematical wisdom. We can say that Whitehead and Russell wanted to show that every mathematical truth could be derived from a small set of fundamental axioms and logical rules. And Gödel essentially showed that their system, or any similar one, could never be entirely complete. But Gödel's work was ahead of its time. It wasn't until later, after mathematicians had a chance to digest what he'd done, that people realized the magnitude of his discovery. He was later celebrated for this genius insight, receiving an honorary degree from Harvard and becoming a legend in the field. Gödel's paper argued a foundational problem of mathematics, which everyone so far had taught to consider elementary geometry as a deductive discipline. To gain more familiarity with what is meant by a deductive discipline, one can think of treating geometry as a system where all truths, theorems, are logically derived from a set of fundamental assumptions or axioms. This approach to geometry was formalized by the ancient Greek mathematician Euclid in his work Elements.
Hold up. There are way too many books, names, and big discoveries flying around here. My brain's officially on strike. Can you simplify this, please?
Absolutely. In Principia Mathematica, written by Alfred North Whitehead and Bertrand Russell, they aimed to demonstrate that all mathematical truths could be derived from a few basic axioms using a deductive approach. However, Gödel's incompleteness theorems showed that no consistent, complete formal system can prove all truths about arithmetic, meaning there will always be some truths that are true but unprovable within the system. This was a major breakthrough that challenged the goals of Whitehead and Russell in Principia Mathematica, which aimed to derive all of mathematics from a set of basic axioms. Gödel challenged the traditional view of mathematics, which treated fields like geometry as systems where truths are logically derived from basic assumptions, a method first formalized by Euclid in his Elements. Are we on the same page with that?
Aye, we are.
So, it's like a mathematical detective story. When mathematicians tried to build a perfect system of geometry, I guess Gödel discovered something mind-blowing. He found that even in math, which we think of as completely logical, there are some truths that we just can't prove.
More or less, yes. Because in geometry, we use these basic building blocks called axioms. They're like the fundamental rules of the game, and for thousands of years, we thought we could use these rules to prove everything about shapes and spaces. But here's the cool part. It turns out that no matter how clever we are, there will always be some mathematical statements that are true, but we can't prove them using our regular tools and methods.
So you are saying it's kind of like having a really complex puzzle where you know the final picture exists, but you can't quite figure out how to put all the pieces together. Even when we use our measuring tools, rulers and protractors, and even when we follow all the logical steps, some truths remain just beyond our grasp.
And this discovery shook up the whole mathematical world. It showed us that even in the most precise and logical system we have, there are still mysteries waiting to be understood. Pretty mind-bending, right?
I wonder if the ancient Egyptians designed the pyramids using a framework that's somehow similar to Gödel's incompleteness theory. Could be an interesting idea to derive from completeness and to explore. Imagine the complexity and structure they might have used. It could be a fascinating line of investigation.
The axiomatic development of geometry made a powerful impression through the ages. Within this framework, whose propositions derive from a deductive discipline, we find that geometry doesn't deal with real objects in an experimental sense. Instead, it works with notions that a proposition must be accepted because they're in agreement with observation. The axiomatic method has shown what may be discovered when we ask where, within the geometric foundations, certain propositions are axioms or postulates. For example, the axiom that through 2 points just one straight line can be drawn, and then deriving from the axioms all the propositions of the system as theorems. What's particularly fascinating is how the axiomatic method and used it to develop geometry in a systematic fashion. This is known as the axiomatic method and is used to develop geometry in a system where propositions are proven through 2 basic tools. the ruler, which measures distances between points, the protractor, which measures angles. Hey, podcast listeners! Let me break down this fascinating academic passage in a way that connects mathematics with everyday understanding. We explore how axiomatic method is used to interact with properties of numbers such as cardinals, which are essentially ways we count and measure sets of things, and negative integers. However, if consider applying axiomatic approach to each area of mathematical thinking, where each of which has a set of its own axioms that are suffice to determine its system, we may have encounter limitations to establish logical consistency in large sets. Number theory is one example of this problem, where the system is too large to be consistent, to capture logical integrity. Therefore, we cannot conclude that a system can be created without an error, and that any branch of mathematical thought are independent from internal contradiction, and that could be a self-contradictory statement. Although Gödel's paper appears to be an opposition to the preconceptions and conventional approaches on the foundation of mathematics, it proposed an understanding of mathematical truth and probability. Gödel's work on fundamental limitations of mathematical systems provided a distinctive approach to mathematical certainty, where we see René Descartes' name on applied algebraic method to geometry to the analytical thinking.
That is fascinating. I guess Gödel changed our understanding of how we approach mathematics. Can you talk about his proof? I guess you have to have a formal system that axiomatic method should be applicable. I mean, it can be arithmetically expressed and has a logical structure.
Well, we can say, for now, that. But there are some mathematical systems that the theorem doesn't apply, are too simple to express basic arithmetic, have non-computable axioms, are already inconsistent, and for mathematical systems that meet the conditions, they must choose between being consistent but incomplete, or being complete but inconsistent. Most mathematical systems opt for consistency at the cost of completeness, and in the next chapter we will talk about the problem of consistency. The problem of consistency. Among Euclid's foundational axioms in geometry, the parallel postulate stands out as particularly significant. This axiom states that through any point not on a given line, exactly one parallel line can be drawn. Unlike Euclid's other axioms, which were considered intuitively obvious, this parallel postulate wasn't readily accepted as self-evident by the Greek mathematicians. They believed it should be possible to prove this statement using the other axioms, which they considered more fundamental and self-evident. This led to numerous attempts to derive the parallel postulate from Euclid's other axioms, marking the beginning of a mathematical quest that would continue for centuries. Can such a proof of the parallel axiom be given from the other axioms? For various reasons, this question was to go unanswered for many centuries, until mathematicians struggled with this question without any apparent failure to construct a proof. That none can be found was finally discovered by means of constructing a model where mean parallel lines can be drawn to a given line through a given point. Mathematics struggled with this question without any apparent success. Modifications of the parallel axiom were eventually supplied to fields of inquiry that had hitherto been cultivated only in a more or less intuitive manner. The overall conclusion that emerged from these critical studies of the foundations of mathematics is that the age-old conception of mathematics as the science of quantity is both inadequate and misleading, for it came clear that proper business of pure mathematics is to derive logical conclusions from any given set of axioms or postulates, regardless of whether these postulates contained in principle to be about anything whatsoever rather than abstract, because mathematical statements can be constructed in principle to be about anything. This development is simply the discipline that draws the conclusions logically implied by given assumptions, regardless of what terms or postulates may be associated with the postulates contained in the premises. Mathematics was thus recognized to be much more abstract and formal than had been traditionally supposed. But things started to change already. Fast forward to the 19th century, and everything changed. Mathematicians like Carl Friedrich Gauss, Janos Bolyai, Nikolai Lobachevsky, and Bernhard Riemann broke away from the traditional approach. Instead of trying to prove the parallel postulate, as authors describes, the impossibility of deducing the parallel axiom from the others was demonstrated by these mathematicians. This outcome was of the greatest intellectual importance in the place where it called attention in the most impressive way to the fact that proof can be given of the impossibility of proving certain propositions within a given system.
It's so strange feeling that system defines the provability.
This led to the creation of non-Euclidean geometries. To better be acquainted with the mathematicians who rolled up their sleeves for the parallel postulate, here is a brief. Lobachevsky developed hyperbolic geometry, a revolutionary form of non-Euclidean geometry. His most significant contribution came from challenging Euclid's fifth postulate, the parallel postulate, by proposing that multiple parallel lines could pass through a point not on a given line. Bolyai independently developed non-Euclidean geometry at around the same time as Lobachevsky. His discoveries showed that alternative geometric systems could be just as logically consistent as Euclidean geometry, fundamentally changing our understanding of mathematical truth and spatial reasoning. Riemann is best known for his contributions to differential geometry, complex analysis, and number theory. His 1854 lecture on the foundations of geometry introduced the concept of Riemann geometry, which extended the ideas of curved spaces beyond Euclidean geometry. This work later became essential to Albert Einstein's theory of general relativity, providing the mathematical framework for understanding space-time curvature. These discoveries didn't just rewrite geometry, they reshaped our understanding of space itself. Riemann's ideas, for instance, laid the groundwork for Einstein's theory of general relativity, a monumental leap in physics. But this story doesn't stop with geometry. It connects to deeper questions about the limits of mathematics itself. This brings us to Gödel's incompleteness theorems in the 20th century. Gödel showed that in any sufficiently complex mathematical system, there are statements that cannot be proven true or false using the system's own rules.
Like the ancient Greek problems of doubling a cube and squaring a circle are classic examples of the limitations of geometry when confined to specific tools and methods. Whether it was possible to construct, using only a straight edge and compass, a cube with twice the volume of a given cube or a square with the same area as a given circle, modern mathematics tackled the hows for the provability rather than the whys of the provability.
Gödel's incompleteness. Theorems shed light on the broader issue. Within any formal system, there are truths that cannot be proven solely using the system's axioms. Similarly, these construction problems lie beyond what's achievable within the constraints of classical geometric tools. The impossibility of solving them was later rigorously proven using algebraic methods, such as showing that doubling a cube requires solving a cubic equation, which is not solvable with straight edge and compass, and squaring a circle involves transcendental numbers, like pi, which are also beyond classical construction.
Pi equals a fascinating measure for geometric. You say pi is transcendental? Can you elaborate, please, and thank you?
Oh, I guess I know. A transcendental number is any number that is not an algebraic number.
Examples of transcendental numbers include pi and Euler's number.
That's it, yes. A transcendental number is a real or complex number that is not algebraic, meaning it cannot be the root of any non-zero polynomial equation with rational coefficients. So to speak, it is a number that is not a root of any polynomial with integer coefficients. They're not many, but very special, I believe. Pi equals 3.1415, E equals 2.718, Euler's constant, and Liouville's number, Liouville's constant, the first proven transcendental number, constructed by Joseph Liouville in 1844, among transcendental numbers. Okay, and continuing. This highlights an important point. Relying solely on an axiomatic approach, as the Greeks did, is insufficient to fully address certain mathematical problems. While axioms provide a logical foundation, they do not always account for deeper algebraic or transcendental properties that define the problem's true nature. In this case, the limitations of their tools and axioms prevented them from recognizing the inherent impossibility of these constructions. This underscores the need for broader mathematical frameworks to complement axiomatic reasoning when tackling complex problems. As the author explains, mathematics is simply the discipline par excellence that draws the conclusions logically implied by any given set of axioms or postulates. In fact, it came to be acknowledged that the validity of a mathematical inference in no sense depends upon any special meaning that may be associated with the terms or expressions contained in the postulate. This shift marked a transition from viewing mathematics as rooted in intuitive truths to recognizing it as an abstract and formal discipline. David Hilbert later formalized this approach in his axiomatization of geometry. He emphasized that the validity of mathematical demonstrations is grounded in the structure of statements and their logical relationships, rather than any inherent meaning assigned to terms like point or line. Hilbert's work underscored that mathematics is not about describing specific objects, but about exploring the logical consequences of assumptions. This evolution in mathematical thought revealed that geometry, and mathematics more broadly, is not confined to physical intuition or traditional notions of truth. Instead, it is a flexible and abstract framework capable of accommodating multiple perspectives and systems. By embracing this perspective, mathematicians unlocked entirely new fields of inquiry and reshaped our understanding of space, logic, and reality itself. Non-Euclidean geometries were initially considered to be in a different category from Euclidean geometry. Their axioms were thought to be false when applied to physical space, and their truth in any context was questionable. The challenge of proving the internal consistency of these systems was recognized as both significant and essential. For instance, in elliptic geometry, Euclid's parallel postulate is substituted with the assumption that no line can be drawn through a point outside a given line that is parallel to it. The question then arises, is the set of postulates for elliptic geometry consistent? These postulates do not align with the space of everyday experience, making their consistency difficult to demonstrate. Simply showing that the theorems already deduced do not contradict each other does not resolve the issue, as the next theorem could potentially lead to a contradiction. Until this question is resolved, one cannot be certain that elliptic geometry is a valid alternative to Euclidean geometry. The very existence of non-Euclidean geometry as a legitimate mathematical framework depended on addressing this issue of consistency. By my understanding, there are certain states that axioms can be contradictory, and it challenges the internal consistency. Although the axioms applied on the geometry of space that leads to contradictions can be reinstantiated on a different category of spatial geometry. So, it's like you are awful at cooking by choice, and by choice the byproduct does not satisfy the expected outcome. So to speak, taste, nutrition basics, visual representation, activity-specific parameters, and so on, and somehow you move on from that state to a state that can have internal consistency. For this example, perhaps you are on a holiday and there is a food, or types of internal states that do not contradict, and so on. A general method for establishing the consistency of abstract postulates was developed. The core idea is to find a model or interpretation where each postulate translates into a true statement about the model. For Euclidean geometry, ordinary space served as the model. This method was extended to find models for other systems, providing a framework to assess the consistency of their abstract postulates. Consider the following set of postulates concerning two classes, K and L, whose specific nature is left undefined except as implicitly defined by the postulates. Any two members of K are contained in exactly one member of L. No member of K is contained in more than two members of L. The members of K are not all contained in a single member of L. Any two members of L contain exactly one member of K. From this small set, several theorems can be derived using standard rules of inference. It can be shown that K contains exactly 3 members. However, the question remains, is the set consistent so that mutually contradictory theorems can never be derived from it? This question can be answered with the help of the following model. Let K be the class of points consisting of the vertices of a triangle, and L the class of lines made up of its sides. And let us understand the phrase, a member of K is contained in a member of L, to mean that a point, which is a vertex, lies on a line, which is a side. Each of the 5 abstract postulates is then converted into a true statement. For instance, the first postulate asserts that any 2 points, which are vertices of the triangle, lie on exactly one line, which is a side. In this way, the set of postulates is proved to be consistent. This geometric model demonstrates that the postulates are consistent. Similarly, the consistency of elliptic geometry can ostensibly be established by a model embodying its postulates. Here, the expression plane in the axioms of elliptic geometry can be interpreted as the surface of a sphere, point as a pair of antipodal points on the surface, and straight line as a great circle on this surface. Each elliptic postulate is then converted into a theorem of Euclidean geometry. For example, on this interpretation, the elliptic parallel postulate reads, through a point on the surface of a sphere, no great circle can be drawn parallel to a given great circle. At first glance, this proof of the consistency of elliptic geometry may seem conclusive. However, a closer examination reveals that the problem has not been solved. It has merely been shifted to another domain. The proof attempts to settle the consistency of elliptic geometry by appealing to the consistency of Euclidean geometry. What emerges, then, is only this. Elliptic geometry is consistent if Euclidean geometry is consistent. This circularity is involved in demonstrating the consistency of a system that challenges the exclusive validity of Euclid. The inescapable question is, are the axioms of the Euclidean system itself consistent? By so far, the answer has been that the Euclidean axioms are true, and therefore consistent. However, this answer is no longer considered satisfactory. We shall return to this issue and explain why it is unsatisfactory. The traditional answer is that the axioms agree with our limited experience of space, and we are justified in extrapolating from the small to the universal. Although much inductive evidence can be adduced to support this claim, our best proof would be logically incomplete. Even if all observed facts align with the axioms, the possibility remains that an as-yet unobserved fact could contradict them, thus undermining their claim to universality. These considerations can show no more than that the axioms are plausible or probably true. Hilbert pursued another approach to address the issue of consistency in geometry. His strategy involved translating Euclid's axioms into an algebraic framework, using Cartesian geometry as a foundation. In this interpretation, geometric concepts were redefined in terms of algebraic relationships. For example, points in the plane were represented as pairs of real numbers, and lines or curves were described by algebraic equations. A straight line was defined as the linear relationship between 2 variables, while a circle was expressed through a quadratic equation. Hilbert demonstrated that these algebraic representations satisfy the axioms of plane geometry. For instance, the geometric theorem stating that 2 distinct points uniquely determine a straight line could be verified algebraically by showing that a linear equation passes through exactly 2 points. Similarly, other geometric properties could be confirmed using algebraic models. This method of establishing consistency relied on transferring problems from one domain, geometry, to another, algebra. However, Hilbert's argument for consistency remained vulnerable to critique because it depended on the assumption that the algebraic framework itself was free of contradictions. This concept demonstrates how geometric shapes, lines, squares, etc., are mapped onto curved surfaces like spheres. These mappings help explain how non-Euclidean geometries, e.g., elliptic or hyperbolic, reinterpret familiar geometric objects under different assumptions, such as curved instead of flat planes.
Are you saying this is like infinite improbability drive?
What is that?
The infinite improbability drive is a fictional, faster-than-light propulsion system from The Hitchhiker's Guide to the Galaxy. It works by manipulating probabilities to such an extent that highly improbable events become certain. When activated, the drive causes the ship to pass through every conceivable point in every conceivable universe almost simultaneously, effectively allowing instantaneous travel between any 2 points in the universe. This process can also result in other highly improbable events occurring, such as objects materializing in unexpected places.
Let's not forget the consistency of any given system. The challenge in proving consistency lies in extrapolating from finite observations to infinite sets. Finite models may verify specific postulates, but cannot encompass all potential cases within an infinite framework. For example, the difficulty lies in the fact that a model can be devised that contains only a finite number of elements. To illustrate this point, consider Euclidean geometry. Finite models can validate certain axioms, but cannot definitively prove their universal truth due to inherent limitations in scope. Similarly, arithmetic systems rely on assumptions about infinite sets, e.g., these integers, which cannot be fully tested using finite means. Ultimately, mathematical proofs are relative to assumed consistencies within their frameworks. While finite models are useful for verifying specific cases, they cannot address all possible scenarios within infinite systems. Author remarks the consistent provability by stating, "The proof is clearly relative to the assumed consistency of another system and is not an absolute proof." Non-finite models are essential for interpreting mathematical systems consistently. A finite model cannot suffice because it would require inspecting an infinite number of elements to ensure consistency, which is impractical. As noted, non-finite models are necessary for the interpretation of mathematical systems. Despite the intuitive clarity and rigor of mathematical reasoning, history shows that contradictions can arise when implicit assumptions are scrutinized. These contradictions have often led to new frameworks or theories to address such issues. For example, the theory of classes, or aggregates, initially appeared consistent but revealed contradictions when applied broadly. This realization prompted mathematicians to refine their assumptions and develop more robust systems. Bertrand Russell constructed a contradiction within elementary logic, mirroring the paradox in the Cantorian theory of infinite classes. The paradox can be summarized as follows. Classes are categorized into two types, those that do not include themselves as members, and those that do. A class that does not include itself is termed a normal class, while one that does is called non-normal. For instance, the class of all mathematicians is normal because it does not contain itself as a member, but the class of all normal classes raises a dilemma. If n, the class of all normal classes, is normal, then by definition it cannot include itself as a member. However, if it is not a member of itself, it must be non-normal. This creates a contradiction because n cannot be both normal and non-normal simultaneously. As stated in the text, in short, n is normal, and only if n is not normal. This contradiction stems from the flawed notion of classes. To resolve this issue, mathematicians have developed systems that avoid such paradoxes by introducing non-finite models or alternative frameworks. These approaches demonstrate that solving foundational problems often requires methods beyond the original scope of the problem.
I am not following. Can you explain our notion of classes?
Let's imagine we are in a neighborhood where there are trees, houses, driveways, and so on, whatever you might feel like adding. There is one distinct house that has some other properties that others have differently. But we also call it a house, and we know that others have differences too. We want to think of this house we pick somehow does not involve in sets of houses, and the notion of the classes can be a constant or generic variant, where there are generic variants.
So how I should be imagining it? Should I be starting from it as a structure that contains elements for life?
That could be a start. We can even think of evolution on the planet, evolution of the planet, and the systems.
Or we can start with something we now picture as a house. There will be houses where the notion of the class, house made different, and the differentiation in the house definition, there might be outliers of classes of sets and classes outline sets.
Oh, I get it. You are saying my definition of a house may have nature settings, and a definition of a house may have virtual settings to someone I know, and there might be a definition of a house that are less definitive to me, and relations of house definition.
So you are saying the system that our notion of the class, house, can have sets of structures.
So here's my question for the audience. How does it feel knowing that math, something we often think of as absolute, is filled with uncertainties and limitations? Does it make you see math as more mysterious or even more exciting? Share your thoughts or questions with us. We'd love to hear them.
Oh, has anyone realized that the problem ancient Greeks, Delian problem, which was about constructing a cube with double the volume of a given cube using only a compass and straight edge? Well, think about if the doubling cube problem is a problem about vectors that have same magnitude. And we think of magnitude is a scalar quantity that represents the size or the length of the vector.
Delian problem. The first major step in the problem of doubling the cube was taken by Hippocrates, probably not long after the problem first appeared. However, it seems likely that the problem was already being considered in a more general form, namely, first, to find a cube whose ratio to a given cube equals the ratio of two given lines. Now, Hippocrates reduced the problem to the following. Second, given two lines, find two mean proportionals between them. For example, given lines A, B, find x, y, such that a colon x equals x, colon y equals v, colon b. Now it is easy with our modern understanding of ratio to see that first and second are equivalent. For a cube x cube equals a colon x cube equals a colon x times x colon y times y colon b equals a colon b. Thus, if we are given a cube with side A and want to construct a cube B A times the volume, we need to construct the cube of side X. Your cube perspective could be different than mine, or the bottom side I see could be perpendicular to the side with respect to my view. So what we know about the class cubes?
I guess we all together can agree on a Rubik cube.
What we can agree that if we want to think of a cube, we can agree that we know what outlines a cube, and we can mathematically say that on 3D plane, a cube looks like this, to us. He who seeks for methods without having a definite problem in mind seeks for the most part in vain. David Hilbert. But on a 3D plane, a cube can be transparent, and to my understanding, and it can be a block of sand. So it's like Rubik's Cube, where there are more instances of same understanding. For example, if I agree seeing the Rubik's Cube on an angle where you agree on the certain characteristics of a cube. In a mathematical sense, we know the scalar quantities are same. If we agree that there is a same scalar quantity between any of the class of cubes, such as when I arrange any sides of cube, where I get 90° between any sides, and sides color can be different, and I have a side color that you can agree, and so on, until all the side colors are agreed upon.
What a journey we've had, moving from the foundational crisis of geometry to the ultimate limits exposed by Kurt Gödel. The central theme that emerges is profound. Every logical system, no matter how rigorous or complete we try to make it, contains its own mysterious boundaries. There will always be truths, whether about numbers, space, or even our own philosophical structures, that are true, yet unprovable from within. This discovery, far from being a failure, is a celebration of intellectual humility and the unending capacity for novelty. Gödel's work, paved the way for Alan Turing's insights into computation, showing that even in the most sophisticated of machines, and by extension, the most elaborate of logical frameworks, there are fundamental limits to what can be automatically proven or decided. It reminds us that consistency comes at the cost of completeness, and that the human ability to step outside a system and recognize its unprovable truth is what keeps discovery alive. The unprovable is not a wall, it is a horizon. This doesn't diminish mathematics. It makes it more beautiful and open-ended. It reminds us that seeking knowledge is a perpetual process. Here, the questions we cannot answer are just as important as the proofs we achieve. It is in these moments of finding the undecidable that we recognize the power of our own creative intuition, which transcends any formalized set of rules. So here's my question for you, fellow surfers of knowledge. How does it feel knowing that math, something we often think of as absolute, is filled with uncertainties and limitations? Does it make you see math as more mysterious or even more exciting? Share your thoughts or questions with us. We'd love to hear them. Thank you for riding this wave of inquiry with me on Inertia Collect. If this conversation sparked a new thought, please consider sharing the episode with someone else who loves to wander through ideas. Until our next dive into the vast landscapes of logic and philosophy, keep seeking, keep wondering, and may you always collect what you love. Take care.